Morning, everybody. Oh, this is just way too quiet. Good morning. Hey, much better. Now you know I'm Jack Barrett. It's my pleasure to provide this presentation for you today. Thank you. I'd like to introduce some other Rigel people who are with me today.
Hi, I'm Brittany. I'm in my third month, and I do sales out of the Tampa, Florida office, the U.S. location. So.
And I'm Amber. I'm also new with Brittany, and I'm out of Pennsylvania.
Not only is she new with Brittany, but she's also new to Rigel Medical. So, as they will quickly tell you, if you have to sit there and listen to me for 75 minutes straight, it's going to get very, very boring. So, as questions come up, and let's talk about it. There's a lot of knowledge in this room. Let's share that knowledge, make it a better presentation. And without further ado, I do want to recognize one individual. There was one person who almost beat me into the room today. So being the first one to arrive, I'd like to present you with a guide.
All right.
On electrical safety testing.
Thank you.
It's the 62353 standard, but also does comparisons to the 601 and NFPA 99. So, thank you. So, what we're going to do today is cover these points. Scope of presentation, a little history as to why we do electrical safety testing. We're going to talk about the standards, classifications, class 1, class 2. We're going to do some dive into testing considerations. We'll do some demonstrations. Up here, we have a little webcam so you can see some testing actually taking place. And summary closing comments, that's where, any remaining questions we can handle, that's where you stand up and give me your rousing applause. And we're good to go. Scope of presentation. So as I kind of said, we're going to talk about the different test standards, IEC 6601, 62353, NFPA 99. And I'm going to talk in depth as to NFPA 99 because U.S. hospitals, that's the test standard that most of you utilize. Injected into this presentation is a lot of updates from the 2018 edition. So the latest and greatest is rolled into this presentation. How many people do the webinar Wednesdays? A couple of you, okay. I did this presentation, I think last April, as a webinar Wednesday, but since then I've added some additional material to it. So hopefully you'll enjoy it. Oh, and most importantly, I missed this second bullet. I'm not here to tell you what your hospital process should be. I'm going to share the test standards with you, but please do not go back and say, hey, Jack Barrett said we should be doing this. Please don't do that. Your hospital process is what you get audited by, whether it's a joint commission or a DND, that's their guideline. Follow your hospital's guidelines. Now, there might be some discussion points because every time in the last 3 revisions of NFPA 99, they do it every 3 years, they've made it simpler and easier each time. And there might be some advantages here. So, you start talking about your bandwidth, how much stuff you can get done in the course of a day. There might be some time-saving opportunities here for you. So if we look at the medical products life cycle, starts off with gaining some customer input, and then it goes into research and development, engineering, into production. And this line and above is primarily where they start to do the test standard, IEC 6601, or the AMI equivalent, ES 6601, and that is the qualification for that medical piece of equipment. Strict guidelines as to what has to be tested, what the limits of testing are, etc. So 6601 really is the manufacturer's guideline. But at this point, this is where it shows up on your loading dock. From that point on, you own that piece of equipment. From preliminary inspection, before it's put on the floor of the hospital or in the ORs, through the PM cycles, through decommissioning. It is the responsibility of biomed, and you guys girls, don't get enough credit for the work you guys do, girls, people, in just the safety and in keeping the health standards high within the facilities. So why do we do safety testing? Well, primarily to help protect you as an operator of the piece of equipment, the nurses, the doctors, and also for the patient. So we'll talk about method of operator protection, MOPE, and MOP, method of patient protection. It's all to be sure that if you come up and you touch something, there's not current sitting there or a potential voltage that would cause current to flow through your body. That's the whole reason behind it. Now, the funny part, and this gets me all the time, most service manuals for different pieces of equipment, surgical generators or whatever, put electrical safety testing last. You stop and think about that for a second. You've already handled a piece of equipment. You've already touched it. So you've already kind of done electrical safety testing through your body. So do it first, not last. And certainly it is the most frequent, most common testing you do. So a little history lesson here. Back in the 70s, his name will pop up on the next slide. A guy by the name of Ralph Nader went into a hospital and discovered that there were some electrical safety issues, shall we say, and kind of wrote an expose. Ralph Nader is a political advocate. So he wrote an article, Microshock Hazard, regarding microshock hazards. And what happens is if there's enough current flow, and it's surprising, we'll have a chart as to what level of current actually can start to cause the heart to go into a resonance, particularly fibrillation. It doesn't take a whole lot of current for that to happen. And unless you fix it pretty quick, you lose the patient. So here's the article he wrote. This is, if you Google this, it's still out there. It was published by the Ladies' Home Journal. Question? Yeah.
You said Ralph Nader was a political advocate. He's actually a consumer advocate.
Yes. Well, he's done some political stuff too.
Yes, but
yeah.
By and large, the largest portion of his existence has been for consumer advocacy.
Yeah. He actually was born about 10 miles away from where I was born. We both grew up in Connecticut. He was a bit older than I was. Not only did he do this, but probably one of the areas where he gained a lot of fame is he wrote an article about an automobile manufactured by Chevrolet called the Corvair. See, the guys with the white hair are going, yeah, I remember that. The young ladies over here are going, Corvair? He meant to say Corvette, right? No. And I mean, the car was pulled off the market. Unsafe at any speed.
They're collectors now.
They are collectors. And you know what? The convertibles were pretty sharp. It was a good looking car. So a question for the team. Why did this get published in Ladies' Home Journal? Any thoughts? Any ideas?
Shock value for a team.
Yeah, and you know, I don't know. So, here's I'm asking a question, and I'd be a terrible attorney because, you're not supposed to ask questions unless you know what the answer is. I don't know the answer to this. I think it was because they gave him a form to move forward with it. Because at that point in time, he wasn't all that well known. But Google it, and this doesn't show up real well here, but they talk about how many people die a year. So his study showed that 1,200 people were electrocuted in hospitals each and every year. So you think about that, right? This is supposed to be the safe place where you're going to go get better, and zap. So elements of preventive maintenance, planned preventive maintenance, because typically this is done on some kind of cycle, usually annually. Starts off with a visual inspection. Morning. If you thought this was just gonna be stand up and have somebody talk to you, no, doesn't work that way. But anyway, we start off with the visual. How many of the issues you find with medical equipment you find doing visual? Majority, right? Yeah, I mean, line cords, like a photo from Ralph Nader there with the tape around the line cord. I mean, that's where most of the issues are. Once you get past there, I mean, you have to do performance certainly on pieces of equipment, but most of your errors will be found during your visual inspection. And then you kind of go line cord, ground continuity, shake the line cord to be sure that there's not any loose connections in there. Insulation testing, if you're doing that, leakage currents, performance testing, data capture, and management. And this is an area that I see a tremendous change within the marketplace, within healthcare. How many folks are keeping track of data on electrical safety? So about half the room. How many people are just recording it and putting it into their CMMS system? The remainder, right? Where do you think that's going? More data, less data? Who thinks more? Who thinks less? Yeah, that's kind of where I think it's going as well. Especially when you look at the NFPA 99 standard. How many people test NFPA 99? Oh, come on. Yeah. As I said earlier, that standard, that test gets a little simpler and easier each year. And one big change in the 2018 revision, they added a lot of additional information, a lot of extra verbiage as to why some of the changes have been made. So it's a pretty interesting read. It's not all that expensive, worthy of perhaps being on your hard drive. So anyway, there we have it. So electrical current, no brainer, requires a closed circuit. There has to be a path for current to flow. So if there was leakage current, now called primarily touch current, it's the latest word for this, sitting on the case, I come up and touch it, my body path gives that potential voltage a way to get to ground, and that drives current through your body. Body model of an individual is 1 k ohm. So we're looking at that. We talk about tissue burns, but really is you start to look at resonance in the heart, and when that heart goes into particular fibrillation, it's not very efficient at putting blood through the body. Hence, you're not getting oxygen through the body. Hence, if that lasts long enough, you don't have to worry about oxygen in the body because you're not breathing anymore. So we talk about all this. But then if you are in particular fibrillation, you have this wonderful device called a defibrillator. And the defibrillators just put 6 amps through the heart muscle and shocks it back into normal sinus rhythm. Anytime you watch a medical show on TV, there's at least 3 or 4 of those guys getting hit every day. So we talked about the levels of current. And if you want to take photos of slides, that's okay. I charge $100 per. Goes into my retirement fund. But no need to worry. If you like to have a PDF for the presentation, after we're done, we'll just scan your badge and we'll email you off the entire presentation. So when we talk about then how shocking the amount of current has to be. Just below 1 milliamp. Man, who's surprised by that number? I was. I mean, 1 milliamp. It's not much. I mean, how many times have you been hit by 120 or 220? Fortunately, your body resistance was high enough, and you probably didn't have the pathway through the heart, which is the most dangerous way, that you did it, but it doesn't take a whole lot. Why this is all important, especially this point right here, 10 milliamps, 10 milliamps. You ever heard freeze on the wire? Right, so if you come into contact with electricity, line frequency are 60 hertz. Europe is 50 hertz. Japan's 50 hertz as well. It doesn't matter. Your muscles can respond to that frequency. So at 60 hertz, at 10 milliamps, your muscles contract. You can't let go of that piece of wire. So your buddy comes over and decides he's going to try to, pull you off, and now you're both knocked down. So you got to get a 2x4. Give them a good wrap, knock them off that wire, have the defibrillator ready if needed, and you're good to go. So as we go up this chart, paralysis, muscular I can talk this morning, breathing problems, fibrillation, 10 or 100 milliamps, microshock, heart defibrillation way up here. So it really, again, driving home how little current it takes. Yes, question.
So I guess this is the shock, right? This is assuming that there's already a pathway across the heart.
Yeah, so, I'll tell you a story. Go off on a quick tangent. I recently went to Ireland, and my dad's family is from County Cork. I learned that there is a castle. It's pretty much ruined at this point, but it was called Barrett Castle, and it's in the middle of a farm. So I want to see this. So we go up there, and it's basically a cow pasture, and there's an electric fence all around it. And the cows are kind of like, whoever thinks animals do not have a sense of humor, they're wrong, because these cows, they had a good morning. So I'm sliding underneath the electric fence, and I feel it brush my back. I don't have any shock. All right. What I failed to think about is I had nice rubber-soled shoes on, so I put my hand down for balance. Ow! I'm on the ground. But it was on this side now, whipped through my right arm, so it didn't go through the heart muscle. Going through the heart muscle is when the most risk occurs early. And those cows were laughing at me. They all were lined up at the fence, staring. Now this is interesting. This is a piece of new information that I came across, because it shows there's a difference between men and women as to the current levels. Why, I don't have a flippant idea, but there is, and it's been proven. The guy who did this study, I think this is a University of California study. So we talked about that let go. For men, 62 milliamps, only 41 milliamps for women. Has to do something somehow, I would say, because of body resistance or something. The same body model was used for testing, but I was surprised. And this shows the body model, the frequency. So this is why when we talk about electrosurgical generators, those are running at 350 kilohertz. So the muscles can't respond to that frequency. You see that's where it starts to fall off right around here. And that's why they use the high frequencies for doing electrosurgery. And yeah, here's a guy, Dalzell. Doesn't talk about where it was. I think this was University of California, pretty sure, did this study. So microshock, macroshock, and microshock is, as we kind of talked about, where the current is flowing through the heart muscle itself. Oh, I thought it might have been down there in the footnote. So leakage current. Whoever came up with that first bullet point, brilliant. Leakage current. Current that is not functional. Not doing any real work, right? There's always going to be some level of leakage current. We measure this in microamps. It's unavoidable because of capacitance and inductance, if something's around a coil of wire and it's metallic. If that coil of wire has current flowing through it, you're going to induce current in the metal object. So it happens, it's always there. Froze from a high potential to a low potential. So in the case of me and the electric fence, the high potential was the fence. The low potential was my hand touching ground, earth, and there was a flow of current. Question or no? Good? Okay. So now, so much of the history. We're going to dive into the standards. So IEC 6601, AMI equivalent ES 6601, 62353, NFPA 99 against, again, the prevalent test standards used here in the US. IEC 61101, anybody ever hear of that one before? Lab equipment. So not typically medical equipment, very close. They look at more potential voltage sitting on a case than touch current or leakage current. But those are the standards that you could run across in your daily endeavors. And then again, just a little bit more on the 61010. So local adaptations of field standards. So remember back on that, the life cycle of a piece of medical equipment, we started off with manufacturing and engineering. That is always tested, as we said earlier, to 6601. That's the qualification process. There are pieces of that, such as high pot testing, where you have to put a high potential voltage on the case of the unit through the electric circuits. Specification for that is 2 times your line voltage plus 1,000 volts. So you're putting 1,500 volts on the case of the unit, and you're looking for leakage current. They do ground continuity or ground bond testing, if that makes, if you're more familiar with that, at 25 amps. If you do that long enough, continuously enough, that piece of medical equipment, you're going to have dielectric breakdown of your insulation. So if you keep high potting something at 1,500 volts continuously, it will fail. So the field standards are a little softer, easier, kinder to the medical device. So we don't do high pot testing at 1,450 volts, whatever it is. We don't do ground bond testing at 25 amps. We do it at 200 milliamps. So long term, in fact, we've done studies where we've taken a ground wire, stranded wire. We've cut off all but just a couple of strands of wire, tested that at 25 amps, passed. Test it at 200 milliamps, it fails. Because at 200 milliamps, that difference in resistance will show up. At 25 amps, man, it burns right through it. So actually, there's not only advantages for the life of the piece of equipment, but it will show you an error faster, quicker than testing it at high current. So these other standards are just variations of the theme, but they're, again, a little kinder, easier. So the biggest one here is 62353, which is a reduced set, if you will, test set of 6601. If you have products coming in from Europe, you look in the service manuals, they will often talk about 62353 testing. That's the field test that they want you to do. Those who do any dialysis machines, they love 62353 test standard because there's a couple of ways you can do that test, which are easier and safer for you as the biomed to do it. And we'll talk about those. And then, of course, bada boom, NFPA 99. So classifications. FDA has their own classifications, which are nowhere similar to these classifications. So from medical device testing, we talk about class 1 devices. the easiest, fastest way to determine if you have a class 1 device? Ground pin. We depend on that ground pin to take any stray currents away from the medical device and shunt them to ground. So anything with a ground pin is tested as class 1. Class 2 is double insulated. So it's, it's the plastic box. A lot of your infusion pumps now are plastic box. So the metal chassis is enclosed in this plastic box, and there is no connection going from the plastic, even the screws holding those two pieces of plastic together, to the chassis. So that's double insulated. And here's a surprise. NFPA 99/2018 says you don't have to test electrical safety in class 2 anymore, which is a big change. I don't know if I personally agree with that, but that's now part of the specification. So when you look on a piece of equipment, you can tell there's always these little symbols. So class 1 is always that ground symbol encased in a circle. That signifies class 1 piece of equipment. The double insulated is the square within a square, kind of saying here's the chassis and there's another square around that, which is the plastic enclosure. Now there's a lot of manufacturers that still test class 2, and they even go as far as to taking the ground probe or the test probe, taking a piece of copper foil or aluminum foil and wiping the chassis, looking to see if they get any current reading on the safety analyzer. Then you see these little symbols. You got the little guy in a box. Then you have the heart. And these talk about the type. B is for body. On the right side, the little paddle say that is defibrillator proof. So it could be part of connected to the patient if need be when they get hit with the 6 amps of current. BF, body floating. So that's kind of why that little square. Think back with what we just talked about class 2, right? Box within a box. There is electrical isolation in the BF. And then cardiac, that's also an isolated situation because, again, you don't want current flow going through that heart. So examples. Oh, and then we have applied parts. Sorry, I missed that. Applied parts is a common term for the manufacturers, and it's very common in Europe. Here it's not as common. We don't have a tendency to talk about applied parts. But an applied part is basically a piece of electrical stuff that comes in contact with the body. Most common there, EKG leads. So that is technically applied part, but we just call it, test leads of some type. So if we look at examples, ECG, EKG, cardiac floating, CF. Defib paddle, BF, body floating. SpO2, the little finger monitor, body floating. Not enough current there really, to do anything, right? But it does come in contact with the human skin, with the human body, therefore it has to be identified something, so it's body floating. Infusion device, classified as CF. When I first saw that, I questioned it. But when you think about it, you have a metal cannula that's going into the vein. Hence, there is a direct pathway to the heart. So infusion devices are CF devices. Anybody surprised by that? Did that make sense when you first saw it? Yeah? And then hospital beds, type B. So IEC 6601-1. Again, this is the qualification standard that every medical device during its design and manufacture has to be tested to. Period. First published in 76, and again, why we're doing all of this is for operator safety and patient safety. So in all of these tests, we start to talk about single fault conditions. Single fault conditions is something went wrong. Not that this ever happens, but there is a tendency sometimes not to unplug something by grabbing, the nice thick part. Quite often it is unplugged how? And not always straight, sometimes, at an upward angle. And since the ground pin is the last pin that exits the socket, and that's by design, because you want that to make first and break last, the ground pin breaks off, falls off. Single fault condition then is open ground. So when we do electrical safety testing, we always talk about single fault conditions. For 6601, single fault conditions are numerous. Open ground, open neutral, reverse polarity. So, take your hot wire and white wire and flip them around. That isn't done often now in the States, because if you do open neutral and you do reverse polarity, you're also doing a power cycle to the piece of equipment, right? And now with more and more computers as part of the system, you gotta wait for that computer to boot up again. So here in the States, we typically don't do reverse voltage. In fact, some pieces of equipment can be damaged. A lot of, oh God, here we go. Ultrasound machines have been damaged by doing reverse polarity testing. So, that's kind of become a no-no. And so here in the States, jump forward a little bit, we do open ground as our single fault condition. That's the only one that you have to do. So we do, as I said, open earth, open neutral, mains and applied parts. So we'll take 110 or 220 volts and we'll put it on those EKG leads and make sure that, they're not electrically breaking down at line voltage. They never see line voltage in operation, but that's how, it's tested to under the 6601. And you go through every one of those. So a lot of safety analyzers have the 6601 test standard built into it. And the complaint that people have is that, man, it has taken forever to do my safety test. Because 6601 will also say, on your EKG leads, test every lead individually to ground. Test every lead to lead to ground. So now you're coming up with, 10 squared tests, and it could take, 15, 20 minutes to do an electrical safety test under this standard, where, with, if you're testing NFPA 99, you're done in under 5 minutes. I mean, it's quick. So applied part testing, 6601. I just kind of talked about this. I'm ahead of myself. So you test each one to ground individually. You test each one lead to lead individually. And what I forgot to say when I was talking about it a moment ago is you do that under normal operating conditions and under every single fault condition. Open neutral, reverse polarity, open ground. So now you just multiplied all those tests by 3. It takes a long time to do electrical safety with this standard.
Excuse me, I thought you said you weren't doing reverse polarity anymore.
So 6601 is still part of it.
Okay.
As we start getting into other tests like NFPA 99, we don't do it here. Some people, there are some biomeds out there, though, older ones, gray hair like me, that still like to do reverse polarity. Yes.
Some manufacturers require us to do that, like Philips, for instance, on the V60s. They actually require you to do the full test.
Yeah. So this is where don't go back and say Jack said that we no. So your hospital process is kind of like that overriding standard now for what you do, right? So if your hospital process is to test to manufacturer specification, then you have to do it. If your hospital process is to test to NFPA 99, you don't have to do it. If you're and these things are always changing. We have a lot of customers now that hardly ever do safety testing anymore. If they have to repair it, they'll do safety testing. But amount of time that safety testing being done is certainly on the decrease, I think. Now, over time, hopefully you have that record history of, that justifies how you can shorten up your test times and such. So it all depends on what your hospital process is. If it says we test to manufacturer specification, then you're going to be doing reverse polarity, yeah.
Didn't the FDA just pass that mandate last year, though? You have to do everything the manufacturer says unless you have an alternative backup.
So there's AEM programs, right? Alternative equipment maintenance. But NFPA 99, 2018, in fact, it went back to 2012 edition. No, you don't have to do it if you're testing to NFPA 99 standard. So, hey, we're talking about 62.353 now. All good on 6601? Anything left on that? I'm going to start giving out books for questions because I got to start pulling information out of you guys. I can see this. So let's see. Questions. I'll autograph these. Like little photos. You had a question?
No, I didn't take one.
I have a question. I guess that was a question.
Oh, I see.
May I have one? The answer would be yes. You had a question. You had a question. You had a question. Anybody else?
Are we done?
No, you haven't been in here long enough to get your credit.
That was a question.
We all can lie.
That was a question.
I actually have another question.
You do?
Yeah. So you were saying that the IEC 16010 for the lab equipment?
Yes.
So just from the standards perspective, we have a lot of times cases where a vendor will bring in like a centrifuge with some of their other equipment, and then we perform, I think we did the FP99, just from what you've been saying.
Mm-hmm.
And so would it make more sense for us to be hospital standards aside, for us to be testing that on the 1601, or is it because it's in a patient area we should be doing it? Yeah.
So this again kind of goes into that. I said I would do NFPA 99 because it is going to a patient area. As you said, I think that's the key. And you want to be sure because they're looking more for voltage on the case than current. Now, if there's voltage on the case, you're going to get current, right? But again, for operator protection and patient protection, I think that would be what I would suggest. Can't take too much. I suggest. Yes. Oh, see, now you start giving away stuff and all these questions.
I don't know if it was covered. What was the difference between the direct alternative and differential, the IEC?
I've been so busy giving out books, I haven't gotten there yet.
Oh, okay.
But you still get one.
All right, cool.
So, now I lost my, there it is. Under the 62.353 test standard, we said it's a little kinder, easier to piece of equipment. But there's 3 different ways in 62.353 that you can test equipment. Direct, alternative, or differential. Direct is simply what you would have done, a direct method of testing. Alternative says take your ground wire, if it's class 1, take your lead wires, put a voltage on all those leads, and look at your leakage currents. So we're still dealing though with, either 250 or 500 volts. There's actually for now. It can be done at 50 volts DC, 100 volts DC, 250 volts DC, or 500 volts DC. So you can have that voltage put on it to do that test. Differential is a neat way to go. It's very safe. And all we're doing in differential is saying, I'm looking at the current going into the unit on the hot wire, black. I'm looking at the current coming out on the neutral wire, the white wire. The difference between those two, my leakage current. Makes sense. Very simple, easy test. But you have to be utilizing the 62353 test standard to do that. All right, so what did I miss on here? No, I haven't missed anything.
So for the 62-353, all three of those criteria have to be checked?
No, you can select whether you want to do direct testing, which is what we're going to do up here. You can select whether you want to do a differential test, which is just you have two current transformers on the main voltage coming in. So whatever is going in and is not coming back out is going somewhere. It's leakage. So you pick which one of those that you want to do. Again, dialysis guys, they love differential. It's fast, simple, easy. And a lot of dialysis machines specify 62353 for the manufacturer's specification and how to test.
One thing that have a different analyzer to do that, because my analyzer just is a simple fail, got an AC plug and it's got, it just measures continuity through the ground plug and it does reverse polarity and all of that, but it doesn't measure any, incoming and outgoing voltage.
So you are absolutely, you already have a book, right? Yeah. You're absolutely correct. You have to have a safety analyzer that has that step standard integrated into it. And then I have one up here that does. And you can just see that, there's a 62353 direct, alternative, differential. So you pick which one that you want to use. But again, you're right. The Dale 601 didn't have that. You just had a rotary switch next to what you said.
You have to kind of reverse switch blows up when you use it.
Especially if you go through quickly. Bang. I suggest people do that more often because I have nice replacements.
That's why the manufacturer wants that too.
Yeah. So only a couple slides on 62353. And now we'll go more into what we typically use here, NFPA 99. So 2018 is the latest revision. They roll it, as we've talked about before, every 3 years. It's the most common one used for U.S. hospitals. And the interesting thing here is I think there's 32 states that say by state law you have to use NFPA 99 as your test in the hospital facility. I don't know about Washington. I know California says it. But when you think about the speed of our government systems, they probably have you testing NFPA 99-1997. They just don't get around to updating that stuff, right? So some of the changes that have been put into 99 now. Classification of areas. So there are different areas within the hospital where the risk of electrical shock is more prevalent than in other areas. And you are now allowed to develop a risk assessment depending as to what area you're in. So designate patient care rooms within the facility, part of NFPA 13-4-2, and get right to it. Category 1, most stringent. Makes sense when you look at this stuff, right? ICUs, CCUs, cath labs, OR, ER. Because these are typically, especially OR, could be ER as well. This is when the body is probably at most risk, right? I mean, there's something going on that's bad already. Got fluids, you can have all kinds of things going on. So the risk of electrical safety, risk of electrical shock is higher than anywhere else in the hospital in these areas. Category 2, dialysis, procedural rooms, bedrooms. Cat 3, examination rooms, the dental office. Some people might argue that dental office can be a scary place. I don't know. But those are Cat 3s. And this one you're going to love, because there is a part of the hospital that they have identified in a category that you would not have believed that they identified. So labs, waiting rooms, and the morgue. However, have you ever been in the morgue and, there's still a little gas or something going on in the patient and that patient sits up? That's a high-risk area. Or one of your associates jumps out behind the closet or something. Yes. Category 4. So classifications, just like we talked before, Class 1, Class 2. Class 2, double insulated, the box within the box, got the chassis and the plastic housing around it, shall be permitted to have 2 conductor cords, so you don't need ground. We're not counting on a ground wire, provide that path to shunt off any leakage or touch current. So only 2 prongs, and also within the patient care facility. And there's something coming up here again that will be maybe surprising to some of you. So fixed equipment physically hardwired into the electrical system of the facility. Maybe the good example of that is OR lights, right? You still have to test them because reach up and grab that handle, which is can often be metal, to reposition light, so they still have to be electrical safety tested. But to do that, we do something called point-to-point, because we can't obviously plug it into our safety analyzer. We have to have the ability to take the point-to-point testing, which basically just use kind of like a multimeter, 2 probes, and we'll look at potential and such. So fixed equipment, leakage current should not exceed 10 milliamps. Period. Portable medical equipment, which a lot of the stuff is today, moved around location to location. In the case of infusion pumps, often lost. Go home with the patient, stashed somewhere in the nurse's closet, so they always have one that they know where it is, until you have to go find them to do a PM. And then it's like, got like 90% of them. Where's the other 10%? So here we go, the good stuff. Ground resistance, ground continuity, earth bond, all the same thing. Power cord resistance is measured by connecting one lead of the plug, grounding pin, and the other to an exposed conductive surface. Grounding pin on equipment is the preferred measuring point. So what we're going to do our first demonstration here. And I have enough cords up here where I can get seriously hurt. And what's the current level that I have to worry about before I go? So what we're going to do, we are going to do this. We're going to find my glasses. There we go. All right. Here we go. Watch how quickly this thing powers up. Boom, ready to go. So when you look at safety analyzers, you always have the power coming into the safety analyzer. You have the socket for the device under test, and you have the plates for your test cable. And in this case, there are 2, so you have the ability to do point-to-point testing. We take our test cable, we can connect it to something that is internally connected to the earth ground. So we're going through metal through our ground pin, which is going to the safety analyzer. And I hit this button, and there you have it. in here, in my presentation, I'm thinking it's the next slide. We talk about what the limits are. What does good look like? Oh, look at that. So we're looking at ground bond resistance here. 0.5 ohms. So anything below half an ohm, according to the NFPA 99 standard, is acceptable. Manufacturer's spec, 6601, says 0.3 ohms. Why the difference? Any ideas? Any thoughts? Yeah.
Time, oxidation.
Exactly. So, you know, the manufacturing standard, 6601, you know, everything's nice, fresh, and clean. Fact of the matter is, once equipment is out in the market for a while, you could have some film resistance building up, you could have some oxidation building up. So they've allowed a longer or a wider area for acceptance. So we can have 0.5 ohms, which you end up changing out a lot more line cords if you really follow that. Now this one's good. I mean, this is pretty new. You see it changing a little bit. What I'm supposed to do now is wiggle my cords to see if, you know, there's any loose wires or anything in there. But that's basically the test. We talk about oxidation. I think I have it on a slide in here, but we do something a little different than a lot of other folks. It would be common for us to take this and get a spark, because we have a capacitive discharge circuit that'll just put a little spike of current. If there's any film resistance or whatever, it burns on. We get that question a lot. It's like our safety and their pros sparks. No, it's by design. It's a little zap circuit. So you don't have false errors, you don't have incorrect readings, you don't end up working on something that you probably or maybe not have to work on. So that's just parts of the specification. If you were interested in it, you would have already read it while I was talking. So we do some comparisons here just to kind of give you a feeling as where the different standards sit and, you know, what the acceptable pass-fail numbers are. So as we said, NFPA 99, 0.5 ohms. 6601, 0.3 ohms. So it all depends on what you're testing here. The process that your hospital set up for your test process, that's what we go by. I have a little note there, which zero readings are suspect. Why?
It's an ideal.
It is. And what happens a lot is, especially now with equipment that has a piece of equipment, think like maybe stress tests, you got the treadmill, and you got monitors, you know, looking at heart rate and such, and you have 9-pin D connectors going from unit to unit. If you get zero resistance, it could be because you have a secondary ground path. And we'll touch on that a little bit further, but it's awfully slick if your safety analyzer can pick that up and let you know. Touch current, leakage current. We used to call it chassis leakage. In fact, most of these things will still say chassis leakage on it because this touch current, it's been around for a while in the IEC. Was there a question? I'm sorry, did I miss something? No. So chassis leakage is now touch leakage or touch current. And, you know, just visually, it makes all the more sense in the world, right? You're touching. What's the possibility of a voltage potential there, allowing current to go through your body? So it's a new term for NFPA 99, but it's been used in the IEC standards for quite some time. So this is nothing new. We've already talked about it a couple times. Potential exists if there's a potential voltage sitting on a metal case. You touch it, you provide the path to ground. And we can do as an example of that as well. So home, put power on. Just a little yellow warning that we have current. I'm supposed to, NFPA standard says do this power on, power off. I'll just turn this on for now, just using this as a test mechanism. So there's my ground leakage. I'll go to chassis leakage where it says chassis leakage rather than touch leakage. So there's my normal operating condition. I open up my ground. That's my single fault condition. I'm done. Yeah, power on, power off. And once you do that, both cases in NFPA 99. The other thing that you can take a look at is the voltages coming into the safety analyzer. So what's the voltage, hot to ground, hot to neutral, neutral to ground, because we use that neutral to ground voltage to trigger fault conditions. So if that gets too high, it's probably because we have an isolated power source. We don't really have a ground. And there's different things that you can do to test that. Turn it off, go back home. Test is done. We're happy. So that's that. So here's a big change. Touch current. You should do it normal operating condition, and you had to do it in a single fault condition. It kind of makes all the sense in the world that if it passes in single fault condition, it would pass in normal operating condition. So NFPA 99 now says for your touch current, you only have to test in single fault condition. So the background's open, and that's our only single fault condition in NFPA 99. And I just struck out those two to remind myself to share with everyone that those are the latest additions to the 2018, which came out in April. Cool thing is they're already working on the next edition. And since I subscribe to this stuff, I get heads up notices as to what people are considering for changes. So anyone can go in and say, hey, you know what, this 10.2.2, I think da-da-da-da-da, and it goes into the board for consideration and for other people to comment on. So it's pretty robust, actually, huh? Leakage current, fixed equipment, portable equipment. We already kind of talked about fixed equipment, right? And again, fixed equipment hardwired into the voltage of the facility, OR lights, your CAT scanners, 10 milliamps. Touch current limits, and this again goes back to that change that we only have to test in single fault conditions, because allowable leakage current is higher in single fault condition. So normal operating conditions, touch leakage current used to be 100 microamps. Open up the ground, they say, hey, you know what, single fault condition, you can have up to 500 microamps, and that's allowable. And that's the only test we have to do, not that single fault condition for your touch. How many people are aware of some of these changes? Yeah, Maria, you subscribe?
No,
But your hospital facility has rolled it in?
I work for a manufacturer.
Okay. So without allowing you to have a sales pitch, what do you specify for how you want testing to be done?
62, 353 on the north.
Yeah. Do you specify differential or direct?
I think it's correct.
Yeah. Here I am. But that, now you've earned it legitimately. So you say, well, I step over my tripping hazard. OSHA would not be happy with me up here, let me tell you. So I go into more detail here, as it does in the standard, with how you do it. And again, they've gone into so much more description now with the 2018. It really is pretty neat. And they talk about this switch being open, which is the ground switch. That's your single fault condition. They've also made this one has been there for a while. I think this goes back to 2012 or maybe earlier than that. We talked about testing leads, patient leads in 6601, where each lead is tested to ground individually, and each lead is tested lead to lead. NFPA 99 now says all of those patient leads, tie them together as a single point and test it that way. Normal operating condition, 100 micrograms. Single fault condition, open ground, 500 micrograms. What do you think about that? Did that just really impact your test time? Yeah. You worry about the limits a little bit, though, right? So dive into that. Oops, no, first we're going to talk about this. And I could talk about it here as well. So our limits, 100 microamps, 500 microamps. I guess I could just use the pointer rather than blocking part of the screen. 6601, 100 microamps, 500 microamps, 100 microamps, until we get to cardiac floating. And they only want to see 10 microamps. But if you have a 10 lead device, 10 microamps times 10 leads, 100 microamps, what are we testing to for pass-fail? We're testing 100 microamps. So it kind of is the same thing. Just really impacts your test time. As I said, I mean, we basically did a safety test there. We didn't do patient leads. It'd be one more push of a button. And it took us, certainly less than 5 minutes. And here it is. So again, tie them all together, test it as one point, test with the power switch on the device, and test with the power switch off on the device. Anybody ever, do you guys do that power on, power off testing? Do you see much of a difference? Never ever, right? Yeah? Somebody say yeah?
Yeah, maybe slightly sometimes.
Sometimes?
Probably like 10 microamps.
I think at some point that'll be the next one that'll change in the standard. Because, and I don't do anywhere near the amount of safety testing, you folks do. I do it when I'm, up here doing this kind of stuff. But I seldom see, much difference. So there you have it. So patient leads, and this kind of goes back into where I was talking about cardiac floating, and there is the 10 microamp for CF. What are you guys doing with beds? Are you doing beds now, or is beds now to the maintenance department? Maintenance, yeah. It's kind of still 50-50, I think, But I think the trend there is more maintenance to give you more time to do, this other stuff. IT carts, computer carts that go into the patient vicinity. Do you do testing on that stuff?
Only if they have equipment fixed to it.
Okay.
Dynamax.
Yeah. Interesting. And I see there are a few hospitals that test their IT cards because it's going into that patient environment, and that's the 11 feet or whatever it is. We'll get to that slide as well. But I digress, which sometimes I do. But I always do try to come back. So patient lead testing, here's just a summary, again, comparing the two. Patient isolation or isolation testing. So this is where you put a voltage on your applied parts or put a voltage onto the device. 6601 says, you put mains on your play parts and such. NFPA 99 says you don't have to do that. 62353 gives you 4 different test voltages. They're all DC voltages. 500 volts, 250 volts, 100 volts, and 50 volts. 150 are newer additions. They came out within the last couple of years. So more for more portable equipment and such, smaller equipment. But we don't have to do any isolation testing, putting a high potential. Yeah.
So we definitely use NFPA 99, but we still do that. Is that like a newer edition change, or is that been like a long time?
That one has been around for quite some time. I don't remember exactly when. It might have been. So reverse voltage, I think, was 2012, I think, if I remember correctly. And I think that one was before that. So, yeah.
So,
yeah.
I have a manufacturer that recommends insulation testing, but they don't recommend a high pot, but they do recommend a Mager.
Okay.
Is there a voltage requirement for Mager that they recommend? I heard 500 volts DC. I heard.
Yeah. So
and not to exceed 2 megs. I mean, to be above 2 megs.
Right. So when you're doing isolation testing, you're really looking at it kind of like a breakdown resistance, right? So that's why it's above 2 meg. You can, and the manufacturer should specify what voltage they want that done at. So I really tried to avoid sales pitch. All the equipment that I happen to have up here is mine. In this one and its next brother down, we have the ability to specify what that isolation voltage is. 500 volts, 250, 100 or 50. Other safety analyzers like this one, which is more focused to the NFPA 99, hence 99 as part of the name. It's really focused on NFPA 99 test standards where we don't have to do that. So again, I mean, if you have to do it, it sounds like you do, you just need to be sure that you have the appropriate safety analyzer that allows you to do it. So here, and I already gave this one away a little bit earlier. Class 2, the plastic box outside with the chassis inside. NFPA 99 2018 says you don't have to do electrical safety testing on that anymore. So a lot of your fusion pumps, unless they have a ground pin, which some still do, you don't have to do electrical safety.
We call them a guide pin.
Guide pin?
Yeah, they're not called a ground pin. And they don't go to anything, unlike.
Okay.
Pumps.
Yeah. Probably. Well, then you get the bigger blade and the thinner blade.
Yeah. And
you always take your cutters and you narrow them down so it doesn't matter. That's what we do. So it's just visual inspection now. That's all you have to do. Just a visual. It's supposed to go to what, 11:15? Is that ticket? I think so, right? Sound about right?
No.
11? Oh, geez, I gotta get going. This was also a fairly new change, although it's better documented now. Technically, if your patient brought in a radio or a computer or something else, technically you were supposed to do electrical safety on it because it's going into the patient environment. And technically, the biomed was the one who was supposed to do that. NFPA 99 now says anybody in the hospital personnel can look at it, determine, kind of do a visual. Is it safe? And you don't have to test it.
Did they say anything about having to record that, to document it? 2018
gives you a big out as far as data management. It kind of goes back to that question that we were talking about, you know, where's the market going? They say that is hospital process. They will give, you know, here's the type of data that one might want to record, but it's not a requirement. And it also says, and this has been around for a long time, a lot of time with, you know, third parties, it's like, well, can you do a training class so my guys are certified? Well, sure we can, because the spec just says qualified personnel. Doesn't say whether you need a 2-year degree, 4-year degree, X years of experience, just qualified personnel. Visual inspection, I don't have to tell you about that. Whoops, wrong button. So how about that animation? That's pretty cool, isn't it? So this just kind of goes back and talks about secondary ground. I said we were going to talk about it. I won't have time to demonstrate that for you. We are in downstairs in booth 304 if you want to come by and play with stuff a little bit, because I am going to run out of time. But 1K body model, that's where you want your current to flow to do your electrical safety testing. However, there's a secondary ground, you know, another 9-pin D connector going from here to there. That gives you a ground path that's going to be less than 1K. So current, like water, will take the path of least resistance. So all of your current will go through the 1 ohm resistor. Very little will go through the 1K resistor. The products that you see up here will come up because it expects to see something. They'll give you a warning message. It says, check for secondary ground. So it ensures that, you know, you're not fooled. Because if there was greater than 500 microamps and there was that secondary ground, you look at it, you're going to see a couple of microamps, you're going to go, we're good. But no, because if the procedure room, if that secondary ground was ever disconnected, you got that capability of having leakage current. Bada bada boom. So power cords, look for broken or bent pins, all kinds of, this is just logic. Yeah.
Go ahead, Ryan.
So, in the secondary ground, so like say you got a ventilator, for instance. So when it doesn't specify in the service manual that you have to have the gas hoses connected, but then you got your secondary ground there, that's what we found.
Right. Most hoses are conductive.
Right. And so, general thought, so we should be disconnecting those secondary ground then.
Yeah.
But the equipment hasn't picked up the ground loop.
Right. And that's the problem.
Right.
That's the problem. Because you're going to get an incorrect reading and you think it's good. By him letting you ask that question, you get the book.
Well, thank you.
Color codes, again, I'm going to go quick through some of this stuff. Everybody knows US black, white, green, international brown, blue, green, sometimes with a yellow stripe. IPS, isolated power sources. Hot brown, neutral orange, ground green. Isolated power sources, your ORs are almost always isolated power sources now because it's another safety consideration. That's where the patient is at the weakest moment. If you're going to do electrical safety testing, you cannot do it with an isolated power source because you're going to get bad readings. So you have to test with a normal grounded conductor. Sometimes that means running an extension cord. Sometimes it says in the isolation transformer box, you put a temporary shunt in to take the low end of that transformer connected to ground. Be sure to remove it. But you have to have a ground to test leakage current to ground. And isolated power sources don't have ground. Now you have on the back of a lot of equipment the equal potential point that a lot of people will tie all together and go to, you know, a ground point. So all the equipment are all sitting at a relative same potential, but there's no real ground. Test process kind of goes to the question before, manufacturer's recommendations. Paragraph 10.5.2 and 99 has 15 chapters in it, some dealing with gas, just some chapter 6 dealing with electrical circuits. Chapter 10 is all about electrical safety. Safety testing is required before putting the device into service for the first time or following any repair or modification that might compromise patient safety. So they're really starting to open up the window as how often electrical safety testing has to be done, but it all comes back to hospital process. So data, we talked a little bit about data. Data is good. Data is wonderful if you have an incident, and you have to have data traceability. And that's all I'm going to say on that. So summary and closing comments. I'm done. Thank you. No. There's the handbook 2018, and you can see. I mean, it's not terribly expensive. A couple $100, you're done. So there's the link. As always, you just do it. Amy came out with this book 2015. On the back is the Rigel logo. We sponsored this work. That's a really nice comparison because it talks about 6601. It talks about 62353. It talks about NFPA 99. But you're all experts now anyway. We have the guides. A lot of you have those now. This is a pretty good book. You can get it on Amazon. Any remaining questions? Otherwise, if you want anything from us, there's our family of safety analyzers. There's our contact information. Thank you so very, very much. And if you want a copy of this or you want anything from us, Amber has our little scanner up here. You can scan your card real quick before you exit. And I need to start cleaning up here. Thank you.